Bland-Altman plot in SPSS, Excel, and Jamovi. This video shows two ways to do Bland-Altman plot, or alternatively called mean difference plot in SPSS. Bland-Altman plots in SPSS. Bland-Altman plot is a graphical method to examine whether two different measurement methods agree and whether the two methods can be used interchangeably. An example where the plot can be used is to check whether the recording or the result from an old-fashioned mercury device for measuring blood pressure and a digital up-to-date device for measuring blood pressure. So the plot can be used to determine whether these two instruments, the mercury one and the digital one, can be used interchangeably and they both agree. The plot is a scattered plot in which the y-axis is plotted with the differences between the two measurements and the x-axis is plotted with the average between the two measurements. The plot also had on it three major horizontal lines: the systematic bias line and two lines for the upper and lower limit of agreement. Here in this SPSS data view, we have two measurements, measurement 1 and measurement 2, and to find out whether these two measurements agree, then we will use the Bland-Altman plot. To do that, first we have to generate two variables. The first variable for the differences between the two measurements and the second new variable for the average between the two measurements. And the way to do that is to click on transform and then click on compute variable, and then in the compute variable we're going to give the new variable a name. We call it difference. Then in the numeric expression, drag the first measurement, then add the minus sign and drag the second variable, and then click on OK. A new variable is generated with the differences between the scores for each of the two measurements. To generate additional variable for the average, click on transform and then compute variable. Let's give this variable a name, which is AV for average, and then get rid of the numeric expression here. From the function group, select the statistical group and then select the mean, as we want to generate the average for the two measurements. Drag the first measurement into here, into this place, and then drag the second measurement into the place here, and then click on OK. A new variable is generated, which is the average for each score for the first measurement and the second measurement. So we have here two new variables, the difference variable and the average variable. Those are two important data to build up the plot, Bland-Altman plot. Before we move ahead and construct a scatter plot, we will first look at the difference variable and determine the mean and the standard deviation for the difference. And the way to do that is to click on Analyze, Descriptive Statistics, frequencies, and then drag the difference variable to this box here in the variables, and untick this as this is not needed. For statistics, just tick for the mean. We need the mean, and we need the standard deviation. We are just going to generate these parameters. Here in this small table, the mean and the standard deviation are generated. As we can see here, the mean is equal to minus 0.048, and the standard deviation for the differences is 0.419. Back again to the data view here. Now to generate the scatter plot, click on graphs and then scroll down to scatter plot. Select the symbol scatter and click on define. On the y-axis, drag the new variable, which is the difference between the two measurements, into the y-axis, and the mean between the two measurements into the x-axis. And let's give this plot a name, Bland-Altman Plot. The title for the graph is the Bland-Altman Plot. Click on continue, click on OK. A plot is generated, scatter plot as shown here. Let's do some editing for this graph. Double click on it. Once you double click on the graph, a new window will appear. We're going to get rid of these horizontal lines here. If we double click on them and select this icon here and then click on apply. Now we have the scatter plot here with the y-axis for the differences and the x-axis for the average. To generate the bias line or systematic bias line or the mean difference line, click on the icon here to add a reference line to the y-axis. And if we click on that here, we need to put the position, as we have found out that the mean for the differences is equal to 0.048, and it is in minus, so it is 0.0488. And if I click on apply, a line is generated here. Let's change the color into red, give it a red color, and then click on apply. To generate the lines, horizontal lines for the upper and lower limits of agreement, we need to use the equation which is given here in this Excel sheet. The equation for calculating the upper limit of agreements and lower limit of agreement is the bias or the mean of the differences plus or minus 1.96 multiplied by the standard deviation for the differences. Here I had inserted the difference mean for the data and the standard deviation. And I've already calculated that, so I'm going to omit that and show you how to calculate the limits for agreement. To calculate the upper limit for agreement, insert equal sign here, select the difference mean, and then for the upper we add the plus sign, and then 1.96 multiplied by the standard deviation, and then click on enter. A value is generated which is 0.77. To do the same for the lower LOA, insert the equal sign, select the bias, add the minus sign, and then type 1.96, use the equation, multiply that by the standard deviation, click enter, value of minus 0.87 is given here. So here we have now three values, one for the difference mean, which is already has been inserted into the plot, and the upper and the lower limits of agreement, 0.77 and minus 0.87. Back again to the scatter plot diagram here. To insert the upper limit of agreement, click on the add references or reference line here, and in the position we are going to insert the value for 0.772, and then click on apply, and then let's change the line color and put it here, let's say green, apply. And then for the lower one reference, add a reference line here, and the value for that is minus 0.87, which is the value just calculated. If we click on apply, then change the color in, let's say, blue, select blue, and then click on apply, and then close this one. After closing all the opened window, click on this one and also close this. Back again to the graph here. As shown here in the graph, we have three lines: the red line for the systematic bias, the green line for the upper limit of agreement, the blue one is for the lower limit of agreement. From this plot, it is apparent that the dots are scattered around the red line, which is the systematic bias, and this red lines is as close as possible to the value of 0, which indicates that these two measurements are agreeable. And if we look at the upper and lower limits of agreement, we can see that the data are scattered, most of the data scattered in between these two lines, and a few outliers there. So fairly from this diagram, it is with confidence we can say that these two measurements agree. To double check it, we can run one sample t-test to mathematically confirm our visual observation. And the way to do that is to click on analyze and then scroll down to compare means and proportions, and select one sample t-test. Here we need to drag the variable for the differences, and in the options we will not select anything, and then click on OK. Tables here are generated. As we can see, the mean is minus 0.048 and the standard deviation is given here. In the table for the one sample t-test, p-value is the one to look for, and as shown here, the p-value is greater than 0.05. This indicates that there is no differences between the two measurements, and these two measurements agree, which indicates that there is no bias between the two measurements. To check if there is a proportional bias, then we can do simple linear regression. The way to do that, click on analyze, scroll down to regression, click on linear, then select the difference variable, drag it to the dependent and the average into the independent, and then click on OK. From the regression model here, what is the most important value is to look for is the p-value, which is the significant p-value, and the unstandardized coefficient. We need this as close as possible to 0. And since the p-value is greater than 0.05, we need this to be greater than 0.05. So this indicates that there is no proportional bias between these two measurements. So this graph and these statistical analysis had confirmed that these two measurement methods do agree. Mean difference plot in SPSS, or alternatively called Bland-Altman plot, is a scatter plot. It is a graphical method used to examine whether two measurement methods agree and whether these two measurement methods can be used interchangeably. An example for that is using an old-fashioned mercury-based blood pressure device and using an up-to-date digital device for measuring blood pressure to find out whether the measurement from both devices agree or the measurement or one device can be used interchangeably with another device, then the mean difference plot is the one to use for that. The plot is a scatter plot. The y-axis is plotted with the differences between the two measurements, and the x-axis is plotted with the average between the two measurements. And in the plot there are three major horizontal lines. One line is the bias line, which represent the mean difference, and another two lines for the upper and lower limits of agreement. Here in this SPSS data view, there are two variables, two measurements, measurement 1 and 2. And to find out whether these two measurements agree or can be used interchangeably, then mean difference plot can be used to visualize whether there is agreement between these two measurements. In a previous video clip, I had described one of the method to do it in SPSS. This is a second way to do and to draw the mean difference plot in SPSS. You need to have the latest version of IBM SPSS to do and to plot this graph. To draw the Bland-Altman plot, click on Analyze, scroll down to Descriptive Statistics, and then select the Bland-Altman analysis. A new window will appear to allow drawing of the graph. Drag the measurement 1 to this position and measurement 2 to this position. Click on Criteria. In the criteria, no changes here will be made, so just click on Continue. On the print icon, I'm going to select the mean differences and confidence interval, the agreement limits and confidence interval, and print details of the analysis. Click on Continue and then click on the plot. In the plot, I'm going to take the agreement limits, and then if I click on Continue and then OK, few tables and a plot are generated. From the second table here, it shows that the difference or the mean difference between measurement 1 and measurement 2 is equal to minus 0.049, which is very close to the value of 0. In the next table, the limits of agreement, the lower limit of agreement is minus 0.87 and the limits of agreement or the upper limit of agreement is 0.773. So this table shows the limits of agreement, the lower and the upper, and this table shows the mean difference, which is the bias or that shows whether there is a systematic bias. Moving to the plot here, which is the Bland-Altman plot of differences between the two measurements, as shown here on the y-axis. The differences between the two measurement methods is plotted here, and on the x-axis is the mean between the two measurements. And in the graph itself there are three horizontal lines. The reddish line represent the mean difference or the systematic bias, and the two blue lines here, the upper one and lower one, represent the limit of agreement, upper and lower. We'll do some editing for this graph to get rid of these lines here. So if I double click on the graph, a new window will appear here. Double click on these horizontal lines, select this section here, and then click on apply. Close this and close this again. Back again to the plot. As we look at the plot here, we can see it is a scatter plot with the dot randomly scattered in the diagram, and the systematic bias or the red line is very close to the value of 0, and there are few scores or data points that are outside the upper and lower limits of agreement. Fairly from this graph or plot, we can see that these two measurement methods do agree, and they can be used interchangeably, and there is no systematic bias. To confirm this mathematically, we could do one sample t-test on the difference. Before performing the one sample t-test, we need to generate two new variables in SPSS. Back again to the data view, we need to generate two variables. The first variable is the difference between measurement 1 and measurement 2. The second variable is the average between the measurement 1 and measurement 2. The way to do that is to click on transform, then select compute, then generate a new variable and give it a name of diff for differences, and then in the numeric expression select the first measurement, add a minus sign for subtraction, and then select the second measurement and then click on OK, and back again to the data view here. A new variable is generated for the differences from each score in these two variables. The difference is calculated and recorded here. To generate the average, click on transform, compute variable, and give a new variable a name which is average, and then erase this numeric expression. In the function group, select statistics or statistical, and then select the mean. In this equation here, drag the first measurement into that position and the second measurement into the second, and click on OK, and back again to the data view. A new variable labeled as averages generated here, which is the average between the scores for each of the measurement 1 and measurement 2. So here we have two variables, the difference variable and the average variable. To move ahead and to do one sample t-test, Click on Analyze, scroll down to Compare Means and Proportions, then select the one sample t-test. In this window here, drag the difference into the test variable. In the options, no changes, and we notice here that we are testing that the difference between the two measurement or the variable difference is equal to 0, i.e. the null hypothesis, there is no differences between the two measurements, they are similar, and the alternative hypothesis, there is a difference between the two measurements. If I click on OK, a few tables are generated as shown here. The mean and the standard deviation are calculated for the variable difference. The mean is minus 0.048. Moving to the second table, which is one sample t-test, what is of concern here is the p-value, the significant value. Since the p-value is greater than 0.05, then we will have to accept the null hypothesis, which indicate that there is no differences between the two measurements, i.e. there is no systematic bias, i.e. these two measurement methods do agree. So this confirming our observation from the Altman plot. To find out whether there is a proportional bias, then linear regression can be done. And the way to do that is to click on Analyze, select the regression, and then go for the linear regression in the new window here. For the dependent variable, select the differences, and for the independent, select the average. Then click on OK, and a few tables are generated here from the simple linear regression. What is of most important is the coefficient here. We need to have the coefficient, which is unstandardized coefficient, to be as close as to the 0 value, and here it is minus 0.07, and we need this p-value to be greater than 0.05. So this table indicates that there is no proportional bias between these two methods. So this is the way to perform Bland-Altman plot in SPSS to test whether two measurement methods agree or not. Bland-Altman plot in Excel. Here in Excel sheet, I have two variables, two measurements, measurement 1 and measurement 2. And to find out whether these two measurements do agree and they can be used interchangeably, then we need to draw the Bland-Altman plot. Before doing that, first of all, we need to generate two new variables, one for the differences between the two measurements and another one for the average between the two measurements. And then to calculate the bias, which is the average for the differences, and the upper and the lower limits, and the standard deviation for the differences. To calculate the upper and lower limits of agreement, we will use the formula LOA, limit of agreement, equal to the bias or mean differences plus or minus 1.96 multiplied by the standard deviation of the differences. The first step is to generate a new variable and call it average, AV. To calculate the average in the cell here, insert the equal sign and then type average, and then select the function for the average. In the average function, in between the brackets, select these two score from measurement 1 and measurement 2, and then click on enter. An average for the two values are calculated and inserted here. To do the average for the rest of the scores, just select and then drag toward the end of the data here, and a new variable is generated, which is the variable for the average. Just to do some editing here, and then to generate the second variable for the difference, let's call it differences, diff. To do that, in this cell, insert equal sign, and then select the first score, add the minus sign, then select the second score, and then hit enter. A value is generated, which is the difference between the two scores from measurement 1 and measurement 2. To calculate the differences for the rest of the scores, select, drag, and release toward the end here. As we can see here, there are two variables generated, one for the average between the scores for the two measurements, and the second one is the difference variable, which is the difference between the two measurements. The next step is to calculate the bias for the differences, or the difference variable, and the bias is the mean difference. The way to do that, select the cell here, insert the equal sign, and then look for the average, select the average function, and then select the data, which is the data for the differences variable. The data are selected, and hitting enter will generate a value of minus 0.05. This value is the systematic bias, or the mean difference, and it is in minus. To calculate the standard deviation for the difference variable, in the cell here, insert equal signs, and then type standard, and then select the standard deviation for the sample. Select the range of the data, and the range of the data is for the difference variable. Once the data are selected, hit enter. A value is generated, which is equal to 0.419. Moving ahead to calculate the upper and lower limits of agreement using the equation just mentioned previously. In this cell here, insert the equal sign, then insert the bias, which is the value here. Then for the upper, insert the plus sign, 1.96 multiplied by the standard deviation, which is calculated here, and hit enter. A value of 0.77 is generated for the upper LOA. For the lower LOA, again the same, insert equal sign, then select the bias, then here add the minus sign, and then 1.96 multiplied by the standard deviation for the difference, which is the value, this one. Then hit enter. A value of minus 0.87 is generated for the lower limit of agreement. The next step is to plot the graph for the Bland-Altman, and we are going to use the values for the variable average, differences, and the bias, the lower and upper limit of agreement. Click on insert, and then select the scatter plot here from this icon. Once a scatter plot is selected, then we need to add the data, and the way to do that is to right click and then click on the select data. In this window, we need to insert the variable for the average. Average should be on the x-axis, and the difference should be on the y-axis. Select the variable for the average, click on the data here and select, and then for the series on y values, select the data for the differences. Click on OK, and then click on OK. Back again to the scatter plot. As shown here on the y-axis is plotted with the difference data, and the x-axis is plotted with the average. Going to do a few editing to get rid of the background here and get rid of this background here, and we're going to lower the x-axis. The way to do that is to select the data here. If I click on it, and then format axis appearing here, select the axis value, and let's give it -2, which is the one here. And if I click enter, x-axis is generated here from 0 to 6, and y-axis from -2 to 2. This is the scatter plot, which is the Bland-Altman plot, but we need also to add to it 3 horizontal lines, one for the bias or systematic bias, and 2 for the upper and lower limit of agreement. To draw the horizontal lines in the x-axis section here, select the value of 0 to 6, as the x-axis range from 0 to 6, and the bias is this value here. So we're going to copy that and then insert that here, and also insert that here. If I drag it, it will be autofill. For the upper limit of agreement, which is this one, select this value and then insert that into the cells below. And for the lower limit of agreement, select the value from here and then insert that into the cell here. Drag it to double it into the next cell. Then to draw the horizontal lines, click on the scatter plot and then right click on it, and then select the data, then add new data or series of data. For the bias, select the x value. The x value are from 0 to 6, and the y value is the calculated bias. And then hit OK, and then hit OK again. 2 dots here are plotted, and this is for the bias line. If we click on the dots here and then make a solid line and give it a reddish color, so here we have the what is called the bias line or the systematic bias line. To draw the upper limits of agreement, click on the graph, right click, select the data, then add a new data here, select the values for the x-axis, which is 0 and 6, and select the values for the y-axis, which is the upper values here. Click on OK, and then click on OK again. 2 dots are generated here. Click on the green dots here and change the color to green. To draw the last line, which is the lower limit of agreement, right click on the graph, select data, and then add new, and then select the y and x data point. For the x is 0 and 6, and for the y is the value for the lower limit of agreement. Then click on OK, then click on OK again. 2 dots appear here, click on them, and let's change the color to give it a dark blue. To label the y and x axis, select axis title and then change the axis title into the difference variable here, and for the y axis is the average here, and then the chart title, which is the Bland-Altman plot. If we enlarge this plot, drag it a little bit more, in the plot, three horizontal lines. The red one is the one for the bias or systematic bias, and the upper and the lower for the limits of agreement. From the plot, we can see that the data points are scattered in the graph, and the value for the bias is very close to the zero value, and there are few outliers data point as shown here, and most of the data point are clustered between the upper and lower limits, and there is no any funnel shape of the data distribution. From this plot we can say that these two measurement methods do agree. To confirm this visual observation, then one sample t-test on the difference variable can be performed, and a regression test, linear regression test, can be done to check for proportional bias. This is the way to draw the Bland-Altman plot in Excel. Bland-Altman plot in Jamovi. Here in Jamovi data view, I have two variables, two measurements, measurement 1 and measurement 2. And to find out whether these two measurements agree, then we need to do the Bland-Altman plot. The way to do that in Jamovi is to click on Analyze and then look for a Bland-Altman plot icon. If the icon is not, or the function is not installed, then click on the plus sign here and then select the function to install from the Jamovi library. To draw the plot, click on the Bland-Altman analysis icon here. A new window is shown here. In the new window, drag the measurement 1 to method 1, measurement 2 to method 2, and then simultaneously a table is generated and a scatter plot also is produced. To just do some editing here, I'm going to get rid of the confidence interval and the confidence interval shading and probably proportional bias, and stick with the this final draft of the plot. As we can see here on the y-axis, the difference variable is plotted here, which is the difference between the two measurements, and on the x-axis the means is plotted between the two measurements. There are three horizontal lines. The one which is close to the zero is the line for the bias, systematic bias, and the top one is for the upper limit of agreement, and the lower one is for the lower limit of agreement. From the table up here we can see that the bias, which is the mean difference, is equal to minus 0.0488, which is very close to the zero value, and the lower limit is minus 0.87 and the upper limit is 0.77. So here from the graph or the plot, the data are scattered randomly, and most of the data fit within the upper and lower limits. There are few data points that are outside the upper lower limits. These are outliers. From here it is fairly can be accepted that there is no bias or systematic bias between the two measurements, and both measurements do agree, as the bias here is very close to the zero value. This is a visual examining of whether these two measurements are agreeing. To confirm the observation from the plot, then one sample t-test need to be performed, a statistical method. To do that, we need to generate two new variables. One variable for the differences and one variable for the average. And the way to do that is to click on the data here and then expand this. To generate the first variable, click on compute, and then in the compute section here on the C1, back again to the column C, let's give this a label of difference, and then the equation will be in the equation or the formula box here, going to first add the data for the first measurement and then minus the data for the second measurement. So it is measurement 1 minus measurement 2, and then click on enter. As shown here, a new variable is generated with the difference between the score from the first measurement and the score for the second measurement for the whole data point in the two variables. To generate the average variable for both measurements, again on the column here, let's do compute for D. Let's give it a name AV for average, and the average will be open a bracket, insert measurement 1 plus measurement 2 divided by 2. And if I hit enter, an average between the first score and the second score is recorded here for all the data from both measurement 1 and measurement 2. So here we have two new column or variables, the difference and the average. To check whether there is a bias between the two measurements, then we need to do one sample t-test, and the way to do that is to click on analysis and then t-test and then one sample t-test. For the one sample t-test, drag the difference into the dependent variable box, and as shown here in the description, the test is student t-test, and the hypothesis, the null hypothesis, is that the difference is equal to 0. And looking at the table generated here for the one sample t-test, the p-value is greater than 0.05, which indicates that there is no differences between the two measurements, i.e. both measurements do agree. So the t-test had confirmed that there is no bias between the two measurements, as the p-value is greater than 0.05. Thus we will accept the null hypothesis, which indicate that there is no differences between the two measurements. And finally, to check if there is any proportional bias, then we need to do simple linear regression. To do simple linear regression, we click on the icon for regression and then select linear regression, and in the linear regression drag the differences into the dependent variable and the average into the independent variable. And again, as we can see here from the linear regression, two tables are generated. The most important one is the estimate for the coefficient, which is given here for the average, which is minus 0.07. We need this value to be as close as to the 0, and the p-value is greater than 0.05, which indicate that there is no proportional bias. This is the way to do Bland-Altman plot in Jamovi. If you find this video useful, do subscribe to the channel, leave any comment in the indicated box, and activate the notification bell to receive the recent and latest release into the channel of several different video clip, and click on the like icon and share the video link with others so the channel can expand and improve to include a large scope of different statistical method and how to analyze data using several different statistical packages such as SPSS, Excel, Stata, Jamovi, Statistics, GraphPad, Prism, GPower, Python, and RevMan. If you are a student or a researcher and you have a data, whether it is quantitative or qualitative, and you want to perform statistical analysis on that data using any of the softwares listed here, whether it's SPSS, Excel, Stata, Jamovi, Statistics, GraphPad, Prism, RevMan, GMP, Python, then do contact me to arrange for either a one-to-one private tutor session or a training course on any of these statistical packages. My contact details are given here, so don't hesitate to write to me or email me if you need a private one-to-one tutoring or a training course.